coming. So today, Hyunwoo will talk about reconstructions, right?
Yeah.
Please.
So thanks for the introduction. So I'll start. So I usually working on the external combinatorics, but today is April Fool's Day. So today's topic is more like structural graph theory and algebraic combinatorics.
Which one was the lie?
So yeah, today I'm gonna talking about how to reconstruct the hypergraph matching polynomials. So this is a joint work with Donggyu Kim, who is now in the Georgia Tech as a postdoctoral researcher. And this project was conducted in the last February, and at that time he was the PhD student at the KAIST, supervised under Sang-il. So I'm gonna start with my talk with this very famous conjecture posed by Kelly in 1957 and Steinschwab-Ulam at 1960 independently. So this conjecture is so-called the reconstruction conjecture. They state that every unlabeled and vertex graph can be uniquely determined from the given the multiset of each n-1 vertex induced subgraph. So I usually say that subgraph was the real subgraph, but today's talk, every subgraph is the induced subgraph, since we are in the structural graph theory. Okay, and there are some several progress on this notorious conjecture. The most notable thing is maybe due to the Bolovas in 1990s. So Bolovas proved that almost all graphs are reconstructible. And for some more explicit families, it is known that trace and unit interval graphs and separable graphs without end vertices are reconstructible, and it is still very widely open now. Okay, so this is the reconstruct conjecture, but
wasn't there some restriction or condition, or
what do you mean?
like n is n is something?
Yeah, we don't. So in here, it should be super large. Yeah. Okay, because Bolovas uses the random graph theory, so with high probability, the graphs can be reconstructible. So with high probability, n goes to infinity. So.
I mean, the conjecture itself, right?
In here we don't need it actually. Maybe n should be at least 3 or something, but that's so large. Okay, so. But this reconstruction conjecture is notoriously difficult because it demands that determining all the structural properties of the given unknown graphs. So it is very, very hard. So people are thinking about what about some specific structural properties, such as is there exists the perfect matching, or it contains a Hamiltonian cycle, or it is a cyclical, that kind of things. So in this direction, in 1977, the Todd proved this very nice theorem, which says that the number of perfect graphs can be reconstructible. So it means that we can exactly count the number of perfect matchings of the unknown n vertex graph from each n-1 vertex induced subgraphs. Okay. And this theorem was extended by Godsil in 1981. This theorem actually says that we don't need this many vertices. Actually, n over 2 plus 1 vertices are enough to uniquely determine the number of perfect matchings. And indeed,
n half vertices.
Sorry.
Any n half or
any n half. So this is the floor, n over 2 floor plus 1.
The question is like
every subset of that size.
like
Every subset of roughly half fraction of the vertices.
okay. The complete deck of subs.
Complete deck of this
okay.
many vertices.
oh, I see. So you are talking about the size of induced subgraph.
Size of induced subgraph. So for example, if we have an n as so many. But actually if we know that every deck of n-1, then we know every deck of these many vertices. So indeed, this is the much weaker
Is it?
condition.
So for the number of perfect matchings, that's about it doesn't seem very obvious. Like if you could do the structure, then that's obvious. But if you won't,
Yeah, it is that obvious
No,
one.
no, I think what you're talking about is you can deduce from number of decks from the information about n-1 vertex in the subgraphs.
Yeah, okay,
You
so
can get information about small
Yeah.
area.
yeah. But if you but here we have the complete structure of the n-1 gives us the number of perfect matchings of
Yeah.
n. So if you only know the complete structure of n-2, then you know the number of perfect matchings at n-1, but that doesn't necessarily. It's not clear that it gives the number of perfect matchings at n.
But
Anyway,
the theorem.
Yeah.
the theorem anyways.
Theorem is there.
okay, so for example, when n is 5 and let's consider we have a say C6. When n is 6, then this Godsil theorem implies that if we have a 4 vertex subset, every 4 vertex subset is given, then we can determine the number of perfect matchings in this unknown graph. Yeah, but it does not imply that we can determine the whole structure of the unknown graph, but we can determine the number of perfect matchings.
Is that a tight result?
Yeah, indeed, this is tight, but it will be appear later.
Okay.
Yeah, this result is tight. I mean, tight in a very strong sense. So n over 2 floor, it is not suffice to determine the number of perfect matchings. And indeed, this Godsil's result is more stronger than just regarding about the perfect matchings. So Godsil indeed reconstructs the matching polynomials. So to rigorously state the Godsil result, so I will give a definition of the matching polynomial of a given graph G. So the matching polynomial of G is denoted by m2 g comma x. I will just put this index 2 because now later I will extend this notion to the hypergraph, K-uniform hypergraph. So this m2 g comma x is defined by this formula. This is the alternative signed sum of the p g comma I times x to the n minus 2i, where p g comma I means that the number of the I size matchings in G. Here the size means the number of edges. So, and when I is a 0, then it means an empty set. So in here we usually consider p g comma 0 as a 1. So it means that this matching polynomial is always a monic polynomial. And so by this definition, you can see that this matching polynomial is uniquely determined by this coefficient, and each coefficients are the number of the prescribed size of the matchings in the G. So the reconstructing the matching polynomials are exactly the same, meaning that we can know that almost every information about the matchings. So okay, so now I will give some another definition, which is more like some notational example. So let H be a K-uniform hypergraph, and I will say it as a K-graph. Let CHT, which is a deck, is the multiset of the induced T vertex sub K-graph of H. Okay. So with this definition, we can state the Godsil's theorem. So they say that every n vertex graph G, its matching polynomial can be uniquely determined from the deck of, the size of the vertices is roughly n over 2 plus 1. Okay. And this is tight. So the Spinoza and West very recently proved that this number n over 2 plus 1 is optimal. In other words, they constructed the two graphs, n vertex graphs G1 and G2. They say, and with the different matching polynomial, but this CG1 n over 2 and CG2 n over 2 is exactly the same set. And now then we can ask what about the hypergraphs? Indeed, considering the hypergraph is pretty natural because if we consider the hypergraph analog, then we can in some sense get some result about the clicks. So for example, number of triangle factors and number of K4 factors, that kind of things can be modeled by the hypergraphs. So considering the hypergraph is pretty natural and have some applications on this direction. So now we are gonna talking about the hypergraph analog of this type of the conjectures. So we can ask the analogous question about the hypergraphs, analogous question for the recursive conjecture. So is it true that every n vertex k graph H can be uniquely determined from its complete deck of the size n-1, where k is at least 3? But usually hypergraphs are much more difficult than the graphs, so it is revealed that in 1972, Kokkei proved that for every k at least 3, this hypergraph analog of the reconstruction conjecture is false. And this counterexample have the infinite family. So yeah, so we don't have any hope to this conjecture for the hypergraphs.
That's a question.
What is a K-graph?
I mean K uniform hypergraph.
Ah,
yes.
K uniform.
It's good to ask. Yeah.
Yes. Now our result is the hypergraph analog of the Godsil's conjecture. So we have shown that the hypergraph analog of the reconstruction conjecture is false. But we can ask that, then what about the matching polynomials? So what about the number of perfect matchings in the K uniform hypergraphs? Is it reconstructible? We can ask it this type of theorems, and our result is indeed the extension of the hypergraph analog of the Godsil's result. So for negotiate our result, we will define the K graph analog of the matching polynomial. So let H be n vertex and K graph. Then we define MKHX as this number, where it is still the iterative signed sum, where the each PH, I is the saying the number of I-size matchings in H and times x to the n minus k. Okay. So now we can state our main theorem. So let H be n vertex and K uniform hypergraph. Then this matching polynomial can be uniquely determined from the complete deck of size k minus 1 over k times n floor plus 1. And when k is 2, it is exactly the same to the Godsil's result. And it has several applications. I already mentioned that we can, by using this result, we can reconstruct the graph tiling polynomials. Okay. Yeah.
Is this k minus 1 over k tight?
Yeah, it is tight. I will show you it a bit later.
For all K or?
I mean, for all k, but some restricted n. So, I mean, when n is 0, 1 modulo k, then for this, and then we type real type. Yeah, and to set the applications, I will define this f-tiling polynomial, which is a natural generalization of the matching polynomial, because we can consider the matching is the K2 tiling. So I mean the tiling is simply the at vertex disjoint isomorphic copies of some graph. Okay. So now let G be an n vertex graph and F be a small graph, F be an K vertex graph. Then we can define f-tiling polynomial denoted as the MFGX, where it is the alternative sum of the PFG, where PFG is the number of vertex disjoint I copies of the F in G. So which is the natural the extension of the matching polynomial. Okay.
Are you considering rival copies or just copies?
In here, let me. Yeah, just a copy. Yes.
Okay.
Oh, you mean copy meaning induced copy or
In here, the subgraph sense.
subgraph?
Just the real subgraph sense.
Oh, what was the question? Are you counting what?
The labeled copy, yes, the labeled copy. But
So for instance, if F is a cycle, right, then you have
Yeah,
the
then-
symmetries and
then if we consider the label, then we should the multiple of some of them, but we are not considering about this.
So you just count one.
Yeah, just
In
count to
that
one.
case.
Yeah, up to automorphisms.
So it's just an indicator. Is there I copies, disjoint copies in this subset of vertices?
Mm-hmm.
Not
Yeah.
how many different ones?
Yeah. How many?
Okay.
So the corollary of our main theorem. So let G be an n vertex graph and K is a k vertex graph. Then this F-tiling match polynomial of G can be uniquely determine the complete stack of these many number of the vertices. Because the proof is pretty simple. Indeed, our main theorem can work for the multi-hypergraphs. So it allows the multiple edges. So whatever we have, this is a graph G. Whenever we have F copy in here, we completely replace this F copy into the K uniform edge. And if this F lies on the same vertex set but in a different way, then we, adding this vertex set as a multiple edges.
Wait, you said that you don't care about the ordering, right? So
Yeah, I mean, what I mean is if we have a C4 in here, we don't care about the ordering, but they can be shared the same vertex set but in a different.
then you
C4.
count
Yeah, then
twice?
we have to count it twice. Yeah, because these two are different C4. Okay. Yeah, but it is the unlabeled copy. So yeah, because of this issue, we are allowed the multiple edges. Okay. And in here, then if we model this the F-tiling to the hypergraph model, then in this auxiliary hypergraph, each matchings are exactly the correspond to the F-tiling. So yeah, by our main theorem, this number is exactly suffices to determine the matching polynomial of the hypergraph, so we can determine these F-tiling polynomials. So do you have any more questions? Okay.
Maybe you can do it either just an indicator on the set of vertices or count it as many times or you could do the labeled one. I mean, the proof doesn't seem sensitive to this at all.
Yeah, I mean,
Like you could just use one edge, or you could multiply everything by 4.
yeah, but one problem is, so this type of the reconstruction, we must consider the unlabeled copies, because if every vertices are labeled, then then it is very easy to determine every structure of the whole vertices, because the vertices are already labeled. So in this direction, we should only consider the unlabeled copies.
Okay.
Okay, so these are our main theorem, and indeed, this the number k minus 1 over k n is the sharp. So whenever n is k and k n is 2 and k divides n, indeed, k minus 1, k divides n minus 1 is okay, but for simplicity, let's say k divides 1. Then there exists we can show that there exists two n vertex k graphs h1 and h2 such that each complete deck of this size is exactly the same, but its matching polynomials are different. We can construct these two hypergraphs whenever we have these condition. So this is the example we call the aligned hypergraph and misaligned hypergraph. So so it says that the first one is we have the common part and two horizontal parts in the upper part, and in here one is in the upper part and one is the lower part. And now let's show that let's check that firstly they have the different matching polynomial. Because of the parity issue, in any cases, one of them have a perfect matching, but the other cannot have the perfect matchings. Because for example, in here, we can choose this one, and then this. It has a perfect matching, but in here we cannot have the perfect matching in here. Yeah. Oh.
The other way around.
Yeah, the other way. Yeah, sorry. These and these two. So we have a perfect matching, but in here we cannot. Yeah. Yes.
So one of them has perfect matching, the other does have no perfect matching.
Yeah, because of the parity issue.
Mhm.
And indeed, we can show that these two have the same deck of the given size. So I will just give you the sketch of how to prove it. So basically, one looks like this. This one, and the other one looks like this. And in here, every deck has the vertex exactly this number, k minus 1 over kn. We can easily show that in here, at some point, at least two of these three vertices should be eliminated. Yeah, should be, yeah, doesn't contain in some the one of the deck. So what I mean is, for every deck you can pick at here, then there exists one layer, it looks like here, such that at least two of them are not contained. Then it means that since we are in the hypergraph, these two are not contained means that it can be, the whole structure can be separated in two connected components, like this and like this. Then if we swap this one is fixed, and we just flip it, then we can make the one-to-one correspondence to this one, this deck. Okay. So yeah, this is a pretty combinatorial argument. So this is the idea to prove this one. And one remark is I already mentioned that the Spinoza and West shows the sharpness of the graph case, but their proof is considerably different from this. So we have an alternative proof. And
I have a question.
yes.
Does this example like similar for all k?
Yeah, similar for okay. So for more higher uniformity, we can add this four uniform, like this. So yeah, maybe many vertices. Yes, and one vertex, and k minus two vertices, and here and one vertex, and so.
So for k equals 2, then
Yeah.
you just think of it as a
Yeah.
graph.
Then we have k is 2. Then we have a path. The first one is a bit longer, and the other construction is the same path, same length path. Then again in here, by the parity issue, if one has a perfect matching but the other cannot has the perfect matching.
Also then, it's 2 disjoint paths.
Yeah, two disjoint paths. So in this case, then if we have n over 2 vertices, then in some sense at least these two should be completely does not contain. Then it is now became a cut. Then we flip it. Then it is one-to-one correspondence to here. Okay, so this is the sharpness. Now let's go to the actual proof. So I'm gonna give a proof sketch of the graph cases. So because our proof is the hypergraph generalization of the Godsil's proof. So the key lemma of the Godsil's proof is using the Godsil's identity, which is appeared in the same paper in 1981. Yeah, so to define the Godsil's identity, we have to collect several notions, like G is a graph and V is a vertex of G. then we let denote that Tg comma V as the so-called the path tree over G rooted in V, where this Tg comma V is defined as its vertex set is the passes in G that is started from V, and each edges is consists of two passes, which is the vertices. That one of them can be obtained from the other by adding an edge. So for example, let's consider we have a triangle, and let's say this is a V. Then each vertices correspond to the passes that start with the V. So obviously the first vertices should be V itself. And the other one can be, let's say this is the U and W. And this is a V, U. And this is the V, W. And V, U, W is the one another candidate, V, U, W, and V, W. Yeah, and these are all the vertex set. And this vertex VU can be extended from V by adding the VU edge. So we add it here. And also VUW can be obtained from VU by adding the edge UW. So we adding an edge. Yeah, like do this. Then this is the path tree of the triangle with respect to V. Okay. So far is pretty simple. And the Godsil's celebrated idea, the identity is the quotient of the matching polynomial of the G minus V and G is same as the quotient of the matching polynomial of the path tree. In some sense, the path tree minus V over the matching polynomial of the original path tree. So why this identity is important in the algebraic graph theory? Because it, in some sense, it gives a bridge between the graph and the trees. So by using this identity, we can bypass many problems arising in the cycles due to the cycles. So using this identity, we can, in some sense, transform our graph into the tree. And usually trees are very well behaved because it has a very nice structure. So many problems can be easily solved. And so this is the Godsil's identity. Now we will collect some folklore results in the algebraic graph theory. I mean, I am also not familiar with algebraic graph theory, but they say that these theorems are folklore. So I will say what it is. So let T be a tree. Then the matching polynomial of the tree is exactly same to its characteristic polynomial. The characteristic polynomial means if we consider the incident matrix of the graph, then you can incident matrix of a graph, and the characteristic polynomial is the characteristic polynomial of this incident graph. Okay. So this is the pretty well-known folklore result.
Wait, so one of them is G, right?
No.
Both are T?
Yeah, both are T. T is a tree. Whenever we consider T is a tree. If we replace T to some general graph, then this does not hold. Yeah.
So the right hand side is chromatic?
No, this one is characteristic polynomial. So the characteristic polynomial is the characteristic polynomial of the incident matrix of the graph. Originations matrix. Yes. You can easily verify this by induction and the cofactor expansions. With respect to induction on the number of vertices.
Why do you need X? Are you deleting one?
X? I mean, this denotes just the polynomial. The polynomial in X.
Okay.
And the another one is let's denote several another polynomials. Let's see G comma X with a generating function. Now generate polynomial generating function of the closed works in G. So in other words, the coefficient of the x to the I is the number of closed work of size I in G. Okay, so that is the generating function of the closed work in G. And let G comma X be the generating function of closed work, but it should be started at V in G. So in other words, the number of the closed work that containing a V.
Sorry.
Yeah.
Does any inequality hold in general graph case?
I don't know, but inequality means that since these are the polynomials, so inequality in which sense? So maybe, yeah, I don't know. Yes. Yeah, but for 3, these are always hold. The another practical result is we can connect the characteristic polynomial and the generating function. So this CV G comma X can be expressed with this formula. Yeah, I'm also not familiar with this, but I searched it, but they say that this is a folklore. Okay. And we need another one. The summation of this type of formula to the every vertices, but in here we should be the matching polynomial. Then it is in a very pretty form 1 over x times this is the derivation of the matching polynomial over the original matching polynomial. Yes. Yeah, these are the 3 folklore results in the early algebraic graph theory. Okay. So now what we have is the Godsil's identity. So by using this, we can transfer the G to some very nice tree, and we have this very nice result which can transfer the matching polynomial to the characteristic polynomial whenever the subject graph is a tree, and we can connect characteristic polynomial to this generating function of the closed work in G. And its summation is looks in a very beautiful form in here. Yeah, now combining everything together, then we can express these to this one. In here, the first inequality using the last one. And now by using the Godsil's identity, we can replace these two in terms of the past tree. Since in here each of the subject graphs are 3, we can and by using the first one, the matching polynomial of 3 is exactly the same to the characteristic polynomial of the 3. So we obtained this result. And now this one is exactly the same as this one as we observed in the second folklore result. And in some sense, this CV TG V comma X means that the sum of the closed works start at V inside in some tree, and exactly and these three are exactly one-to-one correspond to the original tree in the graph G. So actually, these summation count the tree-like works in G. So the tree-like means that if we consider the shadow of the trajectory of the work, then it is a tree. Okay. So using this result, we can, in some sense, we can determine this rational function by counting the tree-like works. Okay.
So it's not completely clear what you mean by tree-like. The
Yeah,
example
okay.
you drew, can't you? Okay, so we
So
start from V, right?
So let's say this is our original graph, and
I don't know. I just wanted to do it with the example you already had here.
in here.
Yes. So
that-
you start from V. You could
we
go
start
down
from G.
the left
and-
branch. So that
Yeah,
means
this
you're
is
doing-
the closed work in the past tree, right?
Yes.
And this is correspond to V, VU, UVW, so UVW. Now we come back, this one, now we come back. And
Okay,
its
and
shadow
what if I
is
continue
exactly
to
this.
VW now?
Yes. And in here, in this, the bit v is the just exactly correspond to this.
No, so I do the red thing,
In
and
here?
then I continue on the other branch, and I go to VW. So now I have all three edges
What do you mean? So
after your red work.
after I have a lead work, then
Yes, why can't I continue to the right branch of the tree?
yeah, we can continue to yeah, we can do these things.
But is okay. This still counts as a tree in the.
Okay. So now, okay. So I skipped the detail because the technical issue. So actually, in here, indeed, we only need to count the n most, the length, the work of the length n most n. Because if we count the length of n most n, then this expression, together with the so-called Newton's identity, it determines every coefficient of this denominator. So indeed, it is enough to count the works in this past tree of length n most n, and each length of n most n is correspond to the tree-like work at here. Okay, since we
Okay.
cannot do, we have the limited size of the length. Okay, yes. And since we are we have a length n most n, and it is a tree-like. So, and each edges are counted in exactly 2 times. So the shadow of this work has vertex n most n over 2. I mean n over 2 plus 1. So that is why we are only did for n over 2 plus 1 vertices to reconstruct these matching polynomials. Does it make sense? Okay. So do you have any more questions? Can I move on? Okay. Yeah. So this is the how the graph case can be improved, and now we want to do is extend this to the hypergraphs, and the key so to this the step is extending the hypergraph. But extending the Godsil's identity to the hypergraph version, and this was already done by myself in the last year. So yeah, so in here I developed some theory for the Godsil's identity, and it is pretty complicated to rigorously write it. So I will just yeah. briefly introduce some key concepts. So the first one is the conflict-free work, which is the subclass of the bird path with some more structural restrictions, and these structural restrictions are depend on the already given linear ordering on the vertex set. Yeah, so it is basically the bird path, but it has a more restricted structural properties. And based on this conflict-free work, we can define the k-work tree, where depending on the based on this conflict-free work, and it is the the k uniform hypergraph analog of the path tree. And our theorem, the last year's theorem, is we have the hypergraph analog of the Godsil's identity with the exactly same form. Yeah, so for example, and also now by using this hypergraph Godsil's identity, we almost done, because by using this we can extend several folklore theorems that I already shown to the hypergraph setting, and we also did some additional ideas. The additional idea is because since we are in the hypergraph, so we cannot consider the adjacency matrix because for hypergraphs, adjacency matrix is not well defined. So to avoid this, our additional idea is giving some cyclic orientation. So we make it as an oriented graph. So we replace each edges to some directed cycle, and each directed cycle on this k-work tree is can be given by using the linear ordering, where this linear ordering is the same linear ordering that is defined in this complete framework. Okay. Yeah. So for example, we have let's say our hypergraph, given hypergraph is a tetrahedron, and tetrahedron the K43, and if we construct the K-work tree for the K43, then it looks like this, and you can show that actually its matching polynomial is exactly the same to the original, the matching polynomial, the quotient of it. Okay. So you see. Yeah. So now I will close my talk with introducing them, mentioning about some concluding remark. So as our corollary of our main result, we reconstructed the f-tiling polynomial for the given graph. So our problem is let f be a given graph, and we want to determine the minimum constant CF, which is strictly smaller than 1, such that for every epsilon there exists the large n0, such that every sufficiently large n, this f-tiling the polynomial can be uniquely determined from the deck of size roughly CF times n, where G is an n vertex graph. So, and our main result implies that this CF is bounded by this number VF minus 1 over VF. But in these cases, we don't know that whether this is tight for the clicks. So we have the tightness for the matchings in the hypergraphs, but we don't know that this is the sharp in general. So I think to determining the CF only for the triangle or K4, it would be very nice. And the last concrete remark is about the Hamiltonicity. So we believe that there exists the constancy which is strictly smaller than 1, and also some existence of a very large n0, such that for every large enough n, the number of Hamilton cycles can be uniquely determined from the deck of the size roughly C times n. And one supporting result for this conjecture is proven by Todd in 1977, and he showed that the number of Hamiltonian cycles in G can be determined the complete deck of size n-1. Okay. So this is what I want to talk on today. So thanks for this.
Thank you. Any questions?
Could you go back to 2 slides before?
Yep.
So why your construction for the tightness for hypergraph matching does not work for, say, triangle or K4 case?
Because if we are in the I already erased. So if we are in the hypergraph setting, then our maybe different color. Our argument is if we can find some these layers such that at least 2 of them are not fit, not chosen, then since we are in the hypergraph, the whole structure may disconnected, so we can flip it. But if we are in the click cases in here like this, some of 2 can be not chosen. If some of 2 are not chosen, but it can be still connected component in the whole structure, so we cannot flip it.
But is it still true for K3?
Yeah, we already tried to checking the case of the K3 and it fails.
remember this example only works when n is a multiple of k.
Yeah.
But you said it is tight when n is 0 or 1 modulo k.
Yeah. Because we have the floor in here. The k minus 1 times n floor. So if n is a k l plus 1, then this l is the negligible. So yes.
So, did you also consider some other polynomial in some other structures, say some polynomial on method? I saw that there is some conjecture on method reconstruction, so I wonder some similarity can be.
To be honest, I'm not so familiar with this direction because why I started this project is so last year I developed the theory for the hypergraph Godsil's identity because I want to disprove the Kant's conjecture, which is something more like a probabilistic combinatorics. And indeed, after I developed this theory and I wanted to to find the more applications with this the Godsil's identity hypergraph out of the Godsil's identity and I searched the Google and they says that it has an application to the reconstruction. So that's why I started this project. So I'm not so familiar with this.
Did you find any other applications of Godsil's identity that
Yeah,
you
they
think,
have.
maybe hypergraph version might be interesting? And there's some open problems.
I mean, there are not so many open problems, but one thing is about the Godsil's identity has an application to the statistical physics. So it is highly related to the so-called the Hellman-Leibniz inequality. And also it has some low concavity over some polynomial. It has a related to the low concavity. And yeah, we can, with the Donggyu, I already tried to extend this type of the Hellman-Leibniz inequality to the hypergraph setting, but we failed.
Any other questions? If not, let's thank the speaker.